Okay, so let's look at some example problems for continuity and one-sided limits. So if we look at each of these functions, we want to comment on if it's continuous at a certain point. So the first function is 1 over x. Okay, we want to know, is it continuous at x equals 0? Okay, is that possible? Well, um, if we look at the graph, obviously, you know, we are not continuous, right? We have one part kind of diving off, one part kind of, again, this is diving, but we have this big break in the gap in the graph. Um, so first off, we look at our rules, right? Rule 1 says that um, we have to have the function defined at the point. So for a, we have f of x equals 1 over x. Well, x can't be 0, so it can't be continuous at 0 either. So not continuous at 0 because it fails rule 1. B says we've got x squared minus 1 over x minus 1. If we look at the graph, again, we have an open hole there, right? So we're not continuous there either. Now, there's a difference um, between A and B. And I will explain that in just a second. So this, it says g of x equals x squared minus 1 over x minus 1. Well, we sit here and we think, well, x can't be 1. So we're not continuous at 1, but what's interesting about this is that we can actually remove the discontinuity in a sense. We can remove it as a vertical asymptote because we can actually factor. X minus 1 is a factor of both numerator and denominator. We can think of this as x plus 1 times x minus 1 if we factor over x minus 1. So this function behaves like x plus 1. That's why it looks like a line. But we still can't be 1. So it's not continuous at 1, but the limits from left and right do agree. C, we have this piecewise function, and what we have here is it says that h of x equals x plus 1, oops, when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. Okay, so for this, we're defined everywhere. We have points everywhere, so that's good. Um, Now, what we want to know, we want to look at these two functions are both continuous. They don't have any discontinuities. It's that simple. You're not dividing by anything. You don't have any square roots or anything, so they're good everywhere. Um, but what we need to know is that in order for this to be continuous, the limits from left and right have to match. So we need to look at the limits of x plus 1 before it gets to 0 and the limits after it gets to 0. So the limit as x approaches 0 from the left of h of x, well, from the left of 0, so it means less than 0, this applies. So we need to use this function. Well, it's as simple as this, guys. All you do is you plug the number in. If this function behaves normally, so like x plus 1, it's a line, completely normal, we just plug our number in. We don't need to plug in 0 minus or anything like that. We just plug in 0. So we end up with 1. And then we have the limit as x approaches 0 from the positive side. So now we're using this of h of x. And that's going to be what happens when we plug in 0 into this, which we also get 1. So we're continuous because we're defined everywhere, and also at this one spot where we're worried, we actually match. And you can see that in the graph, so we are good to go. And then our last one here is the sine of x, or y equals the sine of x. Well, that's just continuous everywhere, right? You're not dividing by anything. You don't have any breaks in the graph. It's completely clean, so it's continuous. So let's look at a one-sided limit. So find the limit of f of x equals square root of 4 minus x squared as x approaches negative 2 from the right. So this would be it written in math language. So we'd say x approaches negative 2 from the right side, so above, of square root of 4 minus x squared. So what we need to know is, well, first off, is negative 2 from the right side. So a number bigger than negative 2, is it on my graph? Okay, well, can I plug a number that is slightly bigger than negative 2? Well, I can. This is part of a semicircle, and you can see this over here. So think about numbers like, negative 1. You can kind of throw that out as a test point. If I did the square root of 4 minus negative 1 squared, um, what I'd end up with is a square root of 5. Or no, excuse me, square root of 3. But if I were to move on the other side, so 4 minus, let's say, negative 3 squared, now this is going to get me the square root of negative 5, which I can't have, right? I can't do this. So I am defined inside this little range, but not on the outside at all. So the limit as I approach from the left side is going to be, I can just plug in negative 2. I can just do that because it exists there. So this is going to equal the square root of 4 minus negative 2 squared, which is the square root of 4 minus 4, which is 0. So this left side of limit does exist, and it is 0. Now there is no limit from the left. Okay, so now it asks us to find the limit of the greatest integer function, which is this. It looks, in case you have a hard time seeing, it looks like this. As x approaches 0 from the left and from the right. Okay, so let's pick a point that we want to use. So let's pick the point 1. Okay, so this point around 1, if we did the limit as x approaches 1 from the left side of f of x, okay, so we're coming from the left side, what number does it look like we're going to? It looks like we're going to the number 1. Or, excuse me, we're going to 0, right, because we're on the 0 line. Looks like that's what our predicted value would be. Now, if we did the limit as x approached 1 from the positive side of 1 of f of x, so now we're going this way. What does our function looks like it's approaching? Well, see, now we're up here, right? Our function is now looking like it's going to the number 1. Okay? Well, remember what we learned from our concept video. If these two limits don't match, then we're not continuous there. Well, obviously that's true. Look, we just have all these breaks in the graph. So this function is not continuous there, but it's defined everywhere, right? There's always a point for this. So this is a good example of a function that is kind of a little quirky and is somewhat normal in a sense, but doesn't have limits at certain places. Okay, so continuity on a closed interval. So discuss the continuity of this graph here. Well, remember, our rules for continuity were this. One, point is defined. Okay, so that's good. As long as our point is defined, we're good. 2, the limit exists. Now, in the case of closed intervals, okay, so in the case where we do have like some sort of closed interval, now this function only exists, the domain of this is only from -1 to 1, okay? So the limit exists. We can use one-sided limits are okay if closed, right? So we are closed. So we can use a one-sided limit here. And so that is true. The one-sided limits do exist in these points, right? We do have a number that we're going to from each side. It's not just infinity or negative infinity. It's an actual number. So we are good there, and that limit does work. And then 3, that that they match, that the function value So the point and limit match, which they do, right? The point exists and it's in the direction where the graph is going and it's right where it's supposed to be. So we're good to go. So this function is continuous on this interval. Okay, so applying the properties of continuity. So we want to say each of these functions is continuous at every point in its domain. Okay, now that is true. Okay, so but let's look at the places that it doesn't have continuity at. Okay, now if we look at f of x equals x plus sine of x, we can look at each part and say, what is that function discontinuous? Because if any part is discontinuous, then it affects the whole graph. Well, x is continuous, sine of x is continuous, so this is continuous everywhere. Everywhere. Then we have f of x equals 3 tan x. Okay, so it's 3 tangent of x. Well, 3 tangent of x is the same as 3 times the sine of x over the cosine of x. So we are limiting in our domain now because we are dividing by a function that can be 0. So we want to know when our cosine is 0. So cosine of x, that's going to be 0 at the following point. So x would be pi over 2 plus pi k. So any number of pi, so half rotations away from pi over 2, would kill our domain. And that is, so we would say something like this. So x can't equal those, right? Because that would make our denominator 0. But we're continuous everywhere else because sine is continuous and 3 is continuous, and we're all good there. So continuous except x can't be these things. So we're continuous everywhere except those. And then we've got f of x equaling x squared plus 1 over cosine of x. This is the exact same thing. We have this function up here is continuous everywhere. The only thing that we have to worry about is our cosine, which again we've talked about before, can't be those things. So we're continuous at every point except for there. Okay, so testing for continuity. Describe the intervals in which each function is continuous. Okay, so A, we've got f of x equals tangent of x. So here again, this is the sine of x over cosine of x. So we know that x cannot equal, from the last example, x cannot equal pi over 2 plus pi k. So we are continuous everywhere except for that. B, so g of x, so this is a piecewise function. G of x equals the sine of 1 over x, or 0. This is when x does not equal 0, and this is when x does equal 0. So what we need to figure out here are is what's going on, basically. What are we doing? Okay, well, in this case, so this function here, we couldn't plug in 0 for it because we would end up with 1 over 0. Now, we don't know, like, we're not going to be able to tell as we go around 0 what our sine is actually going to be. This is a really strange function to look at. Even though we're defined at 0 here, if we were to plug in a very, very small number, so like think about doing one-sided limits here. We're talking about doing like the sine. If x is very, very small, we're talking about this whole thing is going to be negative infinity or infinity. So we don't know what those values are. We have no idea. So this, we don't know if this is continuous at 0. So it's not continuous at x equals 0. Because we have no way of knowing if these two things match or not. C, this is a little bit different. Because this kind of involves the squeeze theorem. So that was really bad. So this is the sine of 1 over x and 0. So, but here's the important thing. It's x times 1 over x. X. Big key here. And that this can't be 0, but this can. Now, this graph is very interesting. The top one, this one down here, we have no, it is behaving, just kind of oddly, but it gets very, very crazy right around 0. And we can't really pinpoint where it is in the middle. Now this graph, however, x times the sine of 1 over x. X is multiplying by it as we go. So we're going to see this kind of squeezing of this function, which is interesting. X is amplifying what sine is as it goes along. So if we think about it this way, we've got kind of two graphs, and this is kind of our origin. Our graph is going to kind of look like this, okay? Because as we get closer to 0, x does also gets closer to 0, and so it's limiting the value of what sine of x can be. And we know that this function, because the sine is approaching 0, x is going to squeeze it. Now, based on the squeeze theorem, we knew that if two functions squeeze together, so we can consider kind of this function and this function separate. If they squeeze together, then we know that it has to pass through this point. So we can actually say, unlike the other one, this is continuous everywhere. Very odd function, but the concept is pretty interesting. And then finally, we're going to do an application of the intermediate value theorem. So we're going to use the intermediate value theorem to show that the polynomial function, so f of x equals x cubed plus 2x minus 1, it has a 0 between 0 and 1. Well, first things we need to know is, where are these points? And I mean, obviously you can use the graph over here to the left as a reference, but we are going to say, so well, f of 0, well, that's going to be 0 cubed plus 2 times 0 minus 1. So that's negative 1. Now f of 1, that's going to be 1 cubed plus 2 times 1 minus 1, which will give us 1 plus 2 minus 1, which gives us 2. Well, that is important. We're going to look, when we look back at this function, we need to decide, is this continuous on this interval? Well, yeah, there's no reason for it not to be, right? We're not taking square roots. We don't have anything bizarre like the greatest integer function. We're not dividing by any functions or anything. So this is, I know 100% sure that this is continuous. You don't even really need to say anything more. Because I'm going from negative 1 all the way to 2, and I'm continuous, I have to pass 0. It's guaranteed that there has to be a 0 in between there. That's what continuity is all about. So because 0 is between negative 1 and 2, f of x must have a 0 in the interval 0 to 1.